Good morning, dear students. Uh, yeah,
Good
good
morning, sir.
morning. Uh, yeah. So I can see 17 students participating to this lecture. On an average, 20 to 20 students are actually are here in Google Meet. And few students they are still actually missing the classes. There may be some problem regarding the attendance. Okay, at the end of the semester. So so they should be very much actually careful. Otherwise, uh, though I am yeah, till now I have not updated your attendance in the ERP, but sooner I will do that. But I have taken the records, okay, of all the previous classes attendances, okay. In this class, so let's see what we have discussed actually in the last class. Uh, so I'm sharing my screen. Yeah. So in the last class, we have analyzed the motion of an undamped free vibration of a single degree freedom system. Okay, so a system which is a single degree freedom system. So we have taken that system as spring mass system, or you can take the system to be a simple pendulum also. Also, one mass will be attached. So the system should have some mass, some stiffness. Okay, so one spring we need to add to the system. Okay, so from the fixed end, with the help of the spring, so the mass was attached, and it was just allowed to oscillate. So it was allowed to oscillate. When it was allowed to oscillate, so some initial displacement was given. So that was x. So it was in the downward direction, and with respect to the mean position, so the body vibrates. So for that system, so in the last class, we have analyzed the motion and we found the equation of motion to be mx double dot plus kx equals to 0, where m is the mass of the system or of the body, x double dot is the second order differentiation, okay, of the displacement. So d square x by dt square with respect to time. Then kx, k is the stiffness and x is the displacement at any time. So after solving that equation, so what we have got? So we have got the final uh, equation of the motion, okay, or we have got the final solution of the equation of motion to be a cosine curve, okay, or to be a sine curve, because cos can be converted to sine, okay. So for that, what you can say, the trigonometric function. So for that, the profile of motion. So we have got the natural frequency omega n. Omega n equals to 2 pi by t. Okay. So for that solution of that cosine or sine function. So this is the natural frequency of the system 2 pi upon t. So where capital T is the time period of vibration. Okay, so because omega n square equals to k by m, so we can write omega equals to under root k by m. So this was also done in the last class. Okay, so you need to remember this formula throughout your vibration course. So omega n square will be equals to k by m for translatory vibration. Okay, because this is a translational vibration or longitudinal vibration. Okay, so omega n equals to under root k by m, where k is the stiffness of the system, m is the mass of the system. So this m is the equivalent mass or the total mass of the system. This k is the equivalent k. Equivalent, there may be numbers of spring. So you need to find out the total spring constant, okay, or the equivalent spring constant. After that only you will be able to find the natural frequency of the system. Okay, so to find out this t, so you can also take the this formula also, 2 pi by omega n. So instead of omega n you will be writing k by m. So 2 pi upon under root k by m. So if you just move it in the upside, so 2 pi under root m by k. So its unit is second. Okay. Then linear frequency. So how to find out the linear frequency? So I have told you that this is the natural frequency or frequency of the system, which unit is radian per second for translational motion. Okay. So the linear frequency is small f. So just like the periodic motion, so it will be small f. So each unit will be hertz, okay, or cycle per second. So f is what? 1 upon t. So 1 upon t means 2 pi, 1 upon 2 pi under root k by m. So inverse of this formula. Okay, means inverse of this time period, it will give you the linear frequency. Okay, so you need to take the frequency uh, by seeing or by observing the unit of the frequency. So if in a problem your frequency is given in cycle per second, then the problem is saying that this is small f. So suppose in a problem the unit of frequency is given is radian per second, then immediately you need to consider that that is omega n or omega. Okay, means natural frequency. If it is a natural frequency, then it will be omega n. Okay, otherwise omega is also there. So basically omega is the external frequency. Okay, so suppose in force vibration, so there will be some external periodic force or some random force. So for that force, so there will be some frequency for that force. So there will be we will be using that omega instead of omega n. Okay, now this is the linear frequency. Now one very important thing which all of you have come across, that is k delta equals to mg. So in the static equilibrium condition, so what you have seen, that when you have added the mass in position 1, if you can remember the earlier diagram, in position 1, so the k delta, okay, so k delta is what? Static deflection. So when you will just give the free vibration, means some initial displacement, this delta will be replaced by x. Okay, that additional displacement we will write here kx. So but here it is delta because this is the static deflection. Okay, so up to the static equilibrium position, so this is the spring force, so which was generated. So and this nature is compressive in nature because it will try to just regain its original position of the body. Okay, so k delta will be equals to mg. So we have discussed this phenomenon. Okay, so in the last lecture. So if you just rearrange this term, so k by m will be equals to z by delta. Okay, so k by m will be equals to z by delta. So instead of this k by m, so you can write z by delta also in some of the problem. Okay, so to solve some of the problem, so if z is given, z is what? Z is the acceleration due to gravity. So if the value is not given, you have to take 9.81. Okay, so like that you need to proceed for a problem. So k by m will be equals to z by delta. Okay, so omega n will be equals to under root k by m or z under root z by delta. So both are same. So this is the expression. So you need to remember for the semester or okay, to solve the problems. Okay, so this is very important problem. So where we have got this formula, so for translational, okay, for translational, till now we have got this formula for translational vibration. Okay, translational or longitudinal vibration. For other types of vibration, so how the natural frequency is found out, so we will see. Okay, and the important thing of the springs, connection of the springs, so we have also studied in the last lecture. So you can see this is what? This is series connection. Okay, means end to end connection of the spring. So one mass is there, so this is single degree freedom system. So here what is actually the important logic to find out the equivalent stiffness? Okay, because k is the spring constant or stiffness of the system. Okay, so to find out the equivalent stiffness, so the basic concept is that here for these two springs, the force which is the spring force which is receiving, okay, by these two springs will be equal actually. Okay, the spring force which will be receiving by these two this one springs will be equal. Okay, why? Because the mass is attached at the end. Okay, so this mg, okay, this mg will be felt by both of the springs equally. So k1 will also feel mg, and k2 will also feel mg. Okay, so that amount of force they will just feel. Okay, so by this concept, the equality of the forces, so you'll be able to find out the springs. Or uh, you can see the total deflection. So when you will be calculating the total deflection, so the total deflection will be delta. Okay, so that delta will be equals to delta 1 plus delta 2, isn't it? So this delta total deflection or the equivalent deflection will be equals to delta 1 plus delta 2. Okay, so what is delta? So delta is what? So delta will be equals to mg by k1, isn't it? And delta 2 will be mg by k2. So mg by k equivalent will be equals to mg by k1 plus mg by k2. So if you just strike out the term mg, then you will get 1 by k equivalent will be equals to 1 by k1 plus 1 upon k2. Then finally you will get this expression. Okay, or you can just rearrange this term also, means yeah, so finally you will be getting that equivalent stiffness. Okay, so why we need to find out the equivalent stiffness? Because to find out the natural frequency, so we need to find out the equivalent stiffness. So k equivalent, I have told you that this formula is for this stiffness of the system. Okay, so total equivalent stiffness, here I am writing k equivalent by m. If there are two or more springs, then you need to find out k equivalent. Okay, so its unit is radian per second. So similarly you can find out the linear frequency also for this system. So f will be equals to, so 1 upon 2 pi under root k by m. So k equivalent you need to write because there are two springs. So finally this will resemble to this system. Okay, just like your k by m system. So if you just add up, you will get k equivalent. So for this, the natural frequency is given by this formula and the linear frequency is given by this formula. So its unit is also hertz. Small f unit is hertz. Omega its unit is radian per second. So I am repeating it again and again because if you don't remember these units, so you will be stuck in some problems. Okay, now you can see the parallel connection of the springs. So when you will say that this connection is parallel, okay, so you need to see the system, you need to analyze the system. See, when the deflection, total deflection will be equals to the individual deflection. Here let's say the deflection after adding the mass is delta. Okay, so that delta will be equals to delta 1 or delta 2. Okay, means this deflection is separately will be equals to the individual deflection of the two springs. Okay, so that is what, that is the parallel connection. Okay, and here it is the end-to-end connection. So deflection, total deflection is not equal to the individual deflection. Total deflection is the summation of this individual deflection for series connection. Okay, means when the total deflection will not be equal to the individual deflection, that connection will be series connection. Okay, so there may be some complex connections of springs, so you need to see the deflection. Okay, you need to feel the deflection, then you will be able to conclude whether the system is in series or in parallel. Okay, so here I have told that concept that the force which will felt by these two springs will be equal, okay, in this series connection, and here the total deflection will be equals to the individual deflection of the two springs, and finally you will get the equivalent stiffness to be k equivalent equals to k1 plus k2. Okay, so by this you will be able to find out the natural frequency. So omega n will be equals to under root k equivalent upon m. So its unit is radian per second, and the linear frequency will be 1 upon 2 pi under root k equivalent upon m. Its unit is hertz. Okay, I think now this concept is clear to you. Okay, so now we will going to solve a few problems. Okay, so let's take this one. See, to obtain, yeah, so for one system will be given. So here this system is given, so both ends are fixed. Okay, So two fixed ends are there. So in between these fixed ends, two springs are connected to the mass. So this will be also single degree freedom system, because the motion will be along this vertical line or axis. Okay, so there may be upward motion, there may be downward motion. Okay, or you can feel that if this is the static equilibrium line, okay, because it is written static equilibrium position. So if you just give some initial displacement, the mass will oscillate with respect to this mean line. So with respect to this mean line, the mass will oscillate. Okay, so here what is given, the stiffnesses of the springs, both the springs are equal, and it is equals to k by 2. Okay, it is equals to k by 2. This mass is here. So initially this system will be like this. So you are asked to find out the equation of motion, and you are asked to find out the equation of motion of the system, and you are asked to find out the natural frequency as well as the linear frequency of the system. So how you will approach? So what you have to write, though I have written only the mathematical part, so you need to write it theoretically also, few parts. So in the solution you will be writing that, let's suppose the mass is displaced x distance or x displacement in a downward direction, because downward direction. Okay, full stop. So after full stop you need to write the same assumption, that all the parameters whatever it will be taken in the downward direction, it will be positive, and all the parameters what will be taken in the upward direction, it will be negative. Okay, so we will be giving some initial displacement to the mass in the downward direction, that is x. Okay, which is a function of t. So when you will be giving some initial displacement, and when you will release, what the body will do, the body will oscillate about this mean position. Okay, so first the downward movement, and then the body itself will try to just reach the midpoint. Okay, the original static equilibrium position, but due to the excess kinetic energy, it will cross it, and again it will move to the same equal upward direction. Okay, equal upward displacement in the upside. Okay, then again it will be moving in the downside. Okay, so then it will oscillate with respect to the static equilibrium position. Now what you need to do, you need to draw the free body diagram. Okay, so when the motion was there in the downward direction, initial displacement was in the downward direction. So for this mass, what you will see, when this was displaced down in the downward direction, this spring will be compressed, isn't it? The length of the spring will be compressed. So what this spring will feel? So it will just exert an tension force in the upward direction, because the mass is suppressing or compressing the spring. So it will try to give some tensile force. Okay, tension force in the upward direction. So the direction of this force is in upward direction. Okay, so this is the direction of the spring force. And what is the value? So spring force equals to F equals to kx. Okay, so here k is what? K by 2. So k by 2x in the upward direction. And when at the same time, when this is displaced in the downward direction, this spring will be elongated, and this spring will try to regain its original shape. So that is why the spring will be giving some compressive spring force. It will be exerting some compressive spring force, which will try to regain the original shape of the spring. So the spring force direction is in upward direction for the upper spring. So k by 2 into x, again the same spring force, k by 2 into x. So both the spring force directions are same. Okay, so the displacement is x, the velocity will be x dot, the acceleration will be x double dot. Okay, so now you need to apply Newton's second law of motion to find out the equation of motion, because in the question you are asked to find out the equation of motion as well as the natural frequency and the linear frequency, isn't it? So if you just apply Newton's second law of motion to this system, so what you will get, that summation of the external forces are equal to m into x double dot. Okay, so what are the external forces? So this one is one of the external forces, this one is one of the external forces. So they both are in upward direction, so both forces will be in negative, the both forces will be of negative direction. Okay, so minus k by 2x minus k by 2x, so these are the external forces. So we will not write the weight force, because that was balanced in the static equilibrium condition by the static spring force k delta st. Okay, So we will not write that force, mg force, okay, because it was balanced in the static equilibrium condition by k delta st. Okay, only we will be writing the external forces. So minus k by 2x minus k by 2x will be equals to mx double dot, because this is the inertia force. Okay, so by Newton's second law of motion, so we will be writing this one. So this equation will give you the equation of motion. So mx double dot k by 2 k by 2, so it will be k, so minus kx. So if you just rearrange, so minus kx will be equals to mx double dot, means mx double dot plus kx equals to 0. Okay, so which was the same equation what you have got in the analysis, isn't it, for a single degree freedom system when the system was connected in this fashion, isn't it? Means this total system k by 2 k by 2 can be converted to this system, isn't it? Because you can find out the equivalent stiffness. So by looking at the system, you will be able to tell whether the system is in series or in parallel. Because see, so when the mass is deflected, so the total deflection will be equals to the individual deflection, because that by same amount, let's suppose the deflection of the mass when it is given displacement xt, so let's say it is delta, so that will be the compressive displacement for this k by 2 spring, and that will be elongation displacement for this spring k by 2, means the deflection of each of the spring will be equals to the equivalent deflection. Okay, so that means they are in parallel. Okay, because in parallel, so we have seen the total deflection of the total mass will be equals to the individual spring. Okay, so here that same thing is happening, that is why it is parallel connection. And in parallel connection, so only by adding the two spring stiffnesses k1 plus k2, means k by 2 plus k by 2, you will get the total spring stiffness. Means you can just convert this system into this equivalent system. Okay, so this system is and this system are basically the same system. Okay, so here this will be the equation of motion. So after the rearrangement, so finally you can write x double dot plus k by m into x will be equals to 0, because k by m, so you need to divide it, divide all the terms by m. So here it will be 1, here it will be k by m. So k by m is what? Omega n square. Omega n is what? Natural frequency. Okay, so below you need to write that omega n will be omega n is the natural frequency of the system. So whose value is equals to omega n square equals to k by m. Omega n will be equals to under root k by m. So here it is written. So omega n is the natural frequency, which is equals to k by m radian per second. So here you will have to write k equivalent actually. Okay, so if you write, oh no, only you need to write k, because k term is there. Okay, this is the equivalent system, so only you need to write k by m radian per second, and here you need to write linear frequency equals to small f 1 upon 2 pi under root k by m hertz. Okay, so if some values are given, then you need to put all the values here, and if the values are not given, then you need to solve it by this way. Okay, so I think this concept is clear to you. So how you will apply the connection of the springs concept, then you will apply the Newton's second law of motion to the free body diagram. Then after that, from that equation, so how you will be able to find out omega n and small f, I think now it is clear to you. Okay, so now I will be checking the chat box, because sometimes you post some doubt and I misses. Okay, I miss that one. Yeah, let us take another example. Oh yeah, one very important thing, so cutting of the spring. So if you just suppose yeah, if you cut one spring, then what will be the equivalent stiffness? Okay, so this is actually very much important for gate purpose. Okay, in gate exam, so you will get this type of question when you will appear in gate. Okay, because consecutively these questions are asked, this division of the springs, okay, or partition of the springs will be given to you. Then what will be the equivalent stiffness, or what will be the natural frequency of the system? So that way the questions are basically asked. So you can see that one spring is given. So in the question, let's say the spring is divided into two equal halves, then what will be the spring constant? Okay, so if this spring when of stiffness k, when it is divided into two equal halves, then its stiffness is becomes twice 2k. Okay, 2k 2k. So individual part stiffness will be 2k 2k when it is actually divided to two half. Okay, two equal half, then their stiffness will be doubled. So you can feel this concept physically also. You can see when there will be a long spring. Okay, so you need lesser force to expand or to contract that spring, okay, or compress the spring. But when there is a small spring, so it is difficult, okay, to pull that spring, okay, or to compress that spring. Because of this tough stiffness, okay, means stiffness is more. That is why the small part will be having more stiffness. So this is a long spring. So when you are making two equal halves, so their stiffnesses will be doubled. Okay, when you are making it two equal halves. Okay, so if the two halves are not equal, then what will happen? Then I will tell you. Okay, so here this concept is written. So now if this same spring is divided into three equal halves, then their stiffnesses will be multiplied by 3 times. Okay, 3k 3k 3k. So these three halves are equal. Okay, so now I am just dividing the spring into two unequal halves. Let's say this length is m, this is n. Okay, m unit, n unit. Then how you will be finding out the stiffness? Okay, the total stiffness was k. Now this ratio is m and this is n. Then you need to write m plus n by m for this half into k. So if value is given, 2 3 is given, so for m you need to put 2, for n you need to put 3. Then 2 plus 3 by 2. Okay, 5 by 2k. Okay, and here it will be 5 by 3k. Okay, so just like that you need to find out the stiffness. Let's say let us consider this example. Okay, 2 and 3, 2 plus 3, 5 by 2k. This part is stiffness will be 5 by 2 k, and this part stiffness will be 5 by 3k. Okay, so it will be more. So here the smaller, I have told you that if these springs are divided into 2:3 ratio for this total length, suppose it is 5 unit. So if it is divided into 2/3 ratio, then the stiffness will be more, because for a smaller spring the stiffness will be more. Understood? So this concept you need to remember. Okay, now let's solve another example. Yeah, so this one will be solving. So basically I was thinking to give this one as assignment. Okay, so okay, I will give this one as an assignment. So you can see this is another problem. There is an inclined plane. Okay, there is an inclined plane which is at an angle of alpha. So on this plane uh, from a fixed end, with the help of the spring, the mass is attached. You can see the mass. Okay, so you are asked to find out actually the equation of motion of this mass, okay, and the natural frequency of the system. Okay. So this will be given. This part will not be given. In the solution, we'll be adding this part, this x displacement. Okay. So only this inclined part will be given. This plane, horizontal plane will be given. This angle angle may be given, or you need to take that angle. This mass, this spring, and the fixed part will be given. Means spring mass system and the planes will be given. Okay. So you will be asked to find out the equation of motion and the natural frequency of the system. So for that, in the solution you need to draw this diagram. So the weight will be acting through the CG, it is mg. So this angle will be alpha, so this will be another component of this mg. So mg cos alpha, this will be mg sin alpha. Okay, so you can resolve this force into two direction, because this plane at an this plane is at an angle. Okay, now to have motion, okay, to have motion, because you are asked to find out the equation of motion. So to have motion, so or to have vibration, so you need to give some initial displacement. So now you are giving some initial displacement in this direction. Okay, in the opposite direction also you can give the displacement, but we are giving the displacement in this direction. Okay, so it is x. So if you are taking the left hand side as a positive, then whatever the displacement will be in the right hand side, you need to take it as negative, or vice versa. Okay, so you can adopt any sign convention. So in one direction if it is positive, in another direction it will be negative. Okay, now what you will see that for this spring, for this weight of this mass, there are two components. One will be this one, which will be vertical to this plane, okay, normal to this plane, which will be balanced by the reaction force, okay, because the mass is on the plane, it is not just getting out from the plane. That is why the reaction of this force mg cos alpha will be equals to that one, so that will be neutralized. So this force is neutralized, so we will not consider in the free body diagram, we will not consider this force. Now another force is there. So in this direction, means you can say that in the direction of the plane, this force mg sine alpha, mg sine alpha will be equals to the static deflection of the spring, means mg sin alpha will be equals to k delta st, okay. So that spring force will, that that k delta st static spring force will be balanced by this mg sin alpha. So that is why we will not consider this component, this vertical component along means with respect to this plane, and the horizontal component with respect to this plane, so we will not consider, okay. So this will be cos component will be balanced by the reaction force, okay, uh, which will be acting opposite to this inclined plane at an angle of alpha, and this force mg sin alpha will be balanced by k delta st, because when the mass is added, so it will be just displaced, okay, there by delta st, okay. So after that we will be giving this deflection, okay, x. So in that condition, the summation of external force will be equals to mx double dot. So that gives will give you the equation of motion, okay, and which is the basis of the Newton's second law of motion. So in this system, so if you apply the Newton's second law of motion, the summation of external force, so only the external force will be what, kx, okay. So kx, so it will be in the right side, because the spring is elongated, so spring force will be acting in the right hand side, means compressive spring force. So minus kx will be equals to mx double dot, because Newton's second law of motion gives that summation of external force will be equals to mx double dot. So if you just rearrange, you will get mx double dot plus kx equals to 0. So this is the equation of motion for this system, okay. So this type of system, so this will be the equation of motion. So finally you will get the natural frequency by writing the equation in this way. So if you divide it by m, so x double dot plus k by m, x equals to 0, this k by m term is equals to omega n square. So omega n is the natural frequency of the system. See, everything you need to write in the problem, though I have just writing in shortcut, but you need to write that this is the equation of motion for the given system. So here so which can be rewritten as x double dot plus k by m x equals to 0. So where k by m will be equals to omega n square. So omega n is the natural frequency of the system. So omega n will be equals to under root k by m radian per second, and linear frequency is f equals to 1 upon 2 pi under root k by m hertz. Okay, so this way you need to find out the natural frequency of the linear frequency. So for every system, try to find out, okay, whatever system it is given, the natural frequency as well as the linear frequency, because this will help you in solving some of the problem. Because in GATE exam, so you will definitely get in, you can see in the alternate years, okay, so you will get some of the problems, okay, just like this type of problems you will get, because these are the basic problems, and in GATE exam only the basic things are asked, okay. So the basic things, though these are the fundamentals, it doesn't uh, uh, actually relate to the directly to the definition, okay. The basics will be clear when you will just read 2-3 books, okay, or when you will go through few lectures, then only your basics will be clear, okay. It does not directly relate to the definition, okay. So the definition, it has got very deeper meaning actually, okay. So if you just mathematically analyze any system, then you will get the fundamentals, then you will get the basics, okay. And if you have the basics actually, then you will be able to solve the GATE problems, okay, or IAS question problem. IAS question problems, some of the problems actually they are directly formula based, okay, or some theory based, but GATE problems are, all the problems are this basic concept, depends on the basic concept, okay. So I think this spring connection of the spring, and this natural frequency and linear frequency concept, and the equation of motion, how to find out the equation of motion for an undamped free vibration of single degree freedom system, it is clear to you. Okay, so there is another problem, so I am giving it to you as an assignment. Okay, not as an assignment, just as a homework. There are three 5 springs, 1 2 3. So these are having k1 k2 k3 stiffnesses, and these 2 springs are having k4 k5. So you need to find out the equivalent stiffness and as well as the mass of the system finally. Okay, finally you need to find out the mass of the system, but to find out the mass of the system, okay, or the frequency of the system, so you need to find out the equivalent stiffness and the mass. Okay, so though you are asked to find out the mass, but here I have found out all those things, Fn, okay, m, all those things are there because it is necessary, otherwise you will not be able to find out m. Okay, yeah, oh yeah, it is given, f is given, sorry, f is given in the system. Okay, so your task is to find out the equivalent stiffness and the mass. Finally you need to find out the mass. The solution is given, just you try. Okay, all the things are given, what is k1 k2 k3, all these things are given. You need to find out this mass. Okay, so this is one homework for you, just you try it, and if you find any difficulty, okay, in solving this problem or earlier problems, so you can just post your doubts, okay, in the Google Classroom also, or in WhatsApp group also, and or you can personally call me at any time. Okay, so okay, dear students, now I will be taking your attendance. How many of you are present actually in today's class? Let me check. Okay, for yeah. Yeah, now you can, yeah, do you have any doubt directly, you can ask me in this class. If you don't have any doubt, then you can leave this meeting. Thank you.